Assalamualaikum. My name is Makhzumi Hakim and my partner is Muhammad Fitri bin Zaijuri. So we are assigned to do the question number 3 for our lab assessment, signal and system. Okay, so today I will present the question number 3 where we analyze the periodic signal using a Fourier series. So the given period here is t equals to 7. So we can see that the signal xt is defined as negative 1.5 with the limit for 0 to 2 and 0 is otherwise, and for ht is negative 4x t over 2 minus 2. So we can see here the signal is time scaled by 2 factor and it shifted to the right 2. So the amplitude is scaled by negative 4. So from the case that I've been introduced, we now draw the graph of xt first with the limit of xt with the xt is negative 1.5 with t equals to 0 and the xt negative 1.5 with the t equals to 2. So we got this shape of graph here, and then for the ht, first we need to time shift to the right with 2 times. So for the ht minus 2, which is it is time shifted to the right by 2. So from here to 4 and go by 2, this is our new point here, and same goes to the next point here. We go to the 1 2. So there is our new limit. And for the ht over 2, which is I say it will be scaled by the factor of 2. We expand since it is lesser than 1, so it is goes like this, 1 over 2t. Okay, and then we continue with the ht with the given of amplitude is negative 4, and this one negative 1.5 is our xt, or we call it as x node. So that means our x node is negative 1.5, should be multiplied by negative 4, we got 6 here. So with our new amplitude is 6, we can plot our ht graph with the same with the new limit we got from the expansion. So this is our ht graph. So now we continue with the Fourier series formula, which is the complex Fourier series coefficient is given by ck is equals to 1 over t integration of ht exponent negative jk omega t dt, with the limit of negative infinity to infinity. So since we have given the t is equals to 7, so we substitute the value of t to 7, and the new limit we got here ht, which is 6 to 2 to 6, when our new ht is 6. So we just simplify the equation here. We got 6 over 7, we got 6 over 7 with the integration of exponent negative j omega naught t dt, and then we integrate the equation, we will get this. Since we integrate exponent, we will still get the exponent, but we need to put the power down. So from here we need to factorize the equation here so that we can apply Euler. So here we can see that we substitute our value of our t with the value of 6 and 2. So since we need to factorize, we can see that from 2 to 6, the middle of 2 to 6 is 4, right? So which is scaled by 2. So we can factorize the equation and it will become like this one. And then from here we can apply Euler and we will get this equation. And now we can simplify the equation with which is we can eliminate the j here and j here, and we can just 2 multiply with 6, got 12 over 7 k omega naught sine k 2 omega naught exponent negative jk for omega naught. So since our omega naught equals to 2 pi over t, so we got our t is equal to 7, we will got this value of omega naught, and we can substitute the value of our omega naught here to this omega naught. And so we can just simplify everything here, and we got this full equation for our ck. Okay, here we continue with our ck when the k is equals to 1. So we substitute our k here with 1, and k here with 1, and k here with 1, and k here with 1. So we will simplify everything, we calculate everything using calculator especially. So we got the value of complex number here, and we need to change it to the polar form. Since we are going to plot the graph of magnitude and phase, same goes with C2, C3, C4, and lastly C5. Since the question need for us to find the coefficient harmonics of 1, 2, 3, 4, 5, so these all values that we got from the calculation shows how each harmonic contributes to the signal. So we continue with the magnitude spectrum graph. So we just plot the value of magnitude here. This is our magnitude, and this is our magnitude, our magnitude, our magnitude, our magnitude here. Okay, so from with the 1, we plot with the first magnitude k1. This is our k, the x-axis is our k, and our y-axis is ck. So we will plot every value that we got, and we got this graph, and continue with the phase spectrum. We did the same thing, just plot the graph with the angle we got from the polar form before, and with the k1 to 5, and we got this graph. Okay, that's all from me, and we will continue with the MATLAB session with Muhammad Zulfitri. Thank you.
Assalamualaikum. My name is Muhammad Fitri, and now I am going to explain the MATLAB part. To begin, let's look at how we define the signal in the first half of the code. First, we start by setting our fundamental parameters, which is a period, and calculating our fundamental frequency from line 6 to 8. And then on line 9, we define the range of from -5 to 5, meaning we are looking at the first 11 frequency components of the signal. Then we move to line 13 and 15. Here we create the actual waveform. It is a periodic pulse with an amplitude of 6 that stays on for a duration of 4 seconds within each period. And then on line 18 until 23, this line generates the first figure, which is our time domain signal, the physical wave we see before any analysis starts. Now we move to the analysis section, where we break the signal down into its frequency ingredients. On line 26 until 28, we initialize an array for our Fourier coefficients and start a loop to calculate each one individually. On line 29 until 31, this is the DC analysis, when we calculate the average value of the signal over one period, which is 3.42 in this case. And then on line 32 until 37, for all other values of we apply the Fourier series integral. This specific method converts the rectangular shape of the pulse into complex number that represent its frequency content. Finally, let's take a look at the part that produces the graph by the frequency domain plots. On line 43 until 48, this code generates the magnitude spectrum. It tells us the strength of each frequency. And then we can see on the graph, the highest peak is at 0, and the strength drops off at the frequency increase. Next, on line 50 until 55, this code generates the phase spectrum. Which is essential for the synthesis part of the process. When we look at the graph, the phase tells us the timing of or shift of each wave. To reconstruct the original pulse, these phases must be exactly as shown to the waves add up to a square shape. And finally, on line 58 until 49, we print the raw numerical values to the command window to verify our visual data. That's all from me. Thank you.